So good evening, participants. Still, that next speaker is not joined. So before that, there is a small presentation. I think
Hello.
yes, madam, please. What is
Sir,
the
can you please resend the feedback link as
okay?
it is not working? Sir, please resend it.
Okay, madam. I will resend the things. Now, please check it, madam. Hello. So you can check that no feedback link.
Yes, sir. Yes, sir. Yes, sir. I will check. Okay. Okay, sir. Thank you.
Ramesh. Ramesh.
Uh,
Shall we
Hello.
start?
Yeah, I'll just share my screen.
Okay. Just a minute. Before that, there is a small introduction. So, good evening, participants. That next speaker, Dr. T. Ramesh from National Institute of Technology, Trichy, is joined.
Hello.
Yes,
Am I audible?
yes, you are audible. Uh, so, just I like to introduce Dr. T. Ramesh. Actually, SAR has taken no yesterday first session. I mean the fifth session on biocomposites in tissue engineering. So today the topic is composite materials in biological and bio-inspired systems from Dr. T. Ramesh, Associate Professor, Department of Mechanical Engineering, National Institute of Technology, Trichy. And no, so sir, no, an introduction is given on yesterday. Then again, I am repeating. So sir did his no BE Mechanical Engineering from University of Madras, and then man master degree ME in engineering design from Government College of Technology, comes under Bardiyar University, Coimbatore. Then he did his PhD in National Institute of Technology, Trichy itself, and he is having nearly 25 years of teaching experience and some 18 years of research experience too. His interested areas are biomaterials, finite element analysis, MEMS, micro devices, powder metallurgy, and so on. So far, SAR has completed uh, sponsored project worth of rupees 1 crore, uh, uh, sponsored by the DST and BHEL Trichy, and SAR has totally 200 publications, and these are the few things. And so far he reached 1895 citations with a H index of 10 and I10 index also. So with these few things, I like to invite Dr. T. Ramesh for this presentation on behalf of my own and the peoples of ISA College of Engineering and Technology and the other participants. Please, sir, please come and start.
Yeah, thank you, Dhanabal, for your introduction. I'll share my screen first. Hope my PPT screen is available.
Yes, 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 it's available. Please continue.
Yeah, yeah. See, the topic what I supposed to talk today, uh, I'll take little time. Before that, as I promised in the yesterday session, we'll see some challenges what I faced in 3D printing of polymers. Um, I'll take 45 minutes to 30 to 45 minutes to cover this topic, and then I'll come back to biocomposites and bio-inspired system. Uh, I think Many speakers would have already been touched the topics like additive manufacturing. The reason because it is a talk of today's research, right? Just a minute. Yeah. I hope many a talk that have been covered in the uh, workshop also on additive manufacturing. But I just wanted to share my own experience with additive manufacturing of polymers as well as polymer composites, what I have printed for various purposes. So additive manufacturing, also termed as 3D printing, usually builds 3D objects by adding materials layer upon layer to form the desired shape. That is a conventional definition of edit 3D printing. So it built the material layer by layer uh, based on the geometrical details it derived from the CAD models, and the coordinate location of many cloud points will be collected, and then it will be converted in the form of G codes and M codes. So that will be control the movement of the extruder as well as the bed, so that uh, a material layer will be oozing out one over another. So AIM is agile and can directly create complex shapes from a digital model, which offers from conventional manufacturing techniques such as milling and molding. Now, AIM is playing the vital role in printing biological components like implants, scaffolds, or it may be a artificial parts or artificial organs like lungs are. So there are many technique has evolved. So based on requirement, a suitable printing technology could be used for printing the biomedical devices. So with the traditional manufacturing processes, whenever making a new component or changing a part design, they require a new tool, mold, or jig. So the a conventional manufacturing method to always think about how to design a tool. What are the various forces acting on the particular tool, control the amount of temperature that could be developed when it is interacting with the material, and what is a mold design and how to fix it by means of jigs and fixtures, how to design it, how to hold the workpiece in the table. So there are many issues or many challenges are there to work with the traditional manufacturing. In the case of a 3D printing, it does not need any physical challenges or changes of equipment or machine after designing the product and software. So that is the greatest advantage the 3D printing technology. Why it is superior now in the manufacturing era. Um, One thing is, as we discussed, like tools are to be designed, molds are to be newly designed, and then jigs and fixtures are to be prepared. But in the case of 3D printing, it doesn't require any physical changes. So thus 3D printing technologies are changing time-consuming as well as labor-intensive manufacturing process. Further, they reduce material waste compared with the subtractive manufacturing approaches. We know that how much amount of material will be wasted when you derive a shape of a component from a regular block, a conventional block. So together with other significant advantages like including flexibility in complex geometry design, tailored property, and customization are also possible. Like functional graded materials are possible in the case of 3D printing. It is highly challenging when you use conventional materials. Means that the certain properties, like for an example, thermal conductivity of a material should be uniformly or changing throughout the length of the component. It is possible in the case of 3D printing, but it is not. I don't want to say that it is not possible, but it is a challenging. In a conventional manufacturing, you need to face many challenges when you are working on such a functionally graded materials. So AM gives new insights not only in the manufacturing field but also in diverse industries such as biomedicine, electrical energy storage, electronics, and robotics. Now there are printers used to print biomedicine. It is like drug delivery system, electrical energy storage. It is possible now, like printing of electronic components are the talk of the today now. Flexible electronics, working on flexible electronics are the challenging now for the 3D printing. So I just rush through these slides because it doesn't require any uh, uh, additional informations I want to share, like how the printing is possible in the case of 3D printing. What is the anatomy of a 3D printer, and then what is the main part behind this particular technology? See, like uh, extruder, filament extruder, or it is a laser or whatever it is. So additive manufacturing technologies are one of the most promising areas in the manufacturing of components. This enables the manufacture of large range of prototypes or functional components with the complex geometries, such as those obtained from topology optimization process or generated from a fitting process in computer design. Now, the topology optimization technique is playing a vital role in optimizing the shape of the object before it is going for any conventional applications. Uh, Say, a very good example is a cycle frame. I think we used bicycles in our olden days with a triangular shaped tubes, right? Tubes are connected by means of a triangular shape. Now you just uh, see that how the size, the shape of the cycle frames are getting evolved. So those are all identified based on the technology called optimization, topology optimization technique, where the material saving without compromising the stresses or and the strain developed in the material is the motivation behind this particular technology. The problem is the topology optimized result would be very complex, because in some location it requires materials, it will distribute materials wherever it is required, and it will remove the material wherever it is not required. So such kind of complex geometry is not at all possible in the case of conventional machines, conventional equipments. But in the case of additive manufacturing, manufactured through layer by layer, it is not challenging now to manufacture such a complex shape. So AM technology is a very broad term encompassing numerical methods such as STL of a photopolymer liquid or fused deposition modeling from plastic filaments, laminated object manufacturing from plastic laminations, and a selective laser sintering from plastic or metal powders. So, however, the FDM technique is of particular interest due to its association to desktop 3D printers. So, FDM forms a 3D geometry by assembling individual layers of extruded thermoplastic element such as ABS or PLA, which have melting temperatures low enough for use in melt extrusion in outdoor non-dedicated facilities. So additive manufacturing, commonly known as 3D printing, refers to a process of creating three-dimensional objects layer by layer from a digital model, CAD, computer design. So unlike traditional subtractive manufacturing methods that involve cutting away materials from a larger block, manufacturing builds up the object progressively, typically using materials such as polymers, metal. I think almost all the category of or the classification of done with the help of this particular technology. Polymer is possible to print. Metals are also possible to print. Ceramics, we are developing a technology for printing ceramics, composites, or even clay models are now printed with the help of 3D printing technology. Uh, so this technology has found applications across various industries, including aerospace, automotive, healthcare, consumer goods, due to its flexibility, cost effectiveness for low volume production, and potential for rapid prototyping. See, I recently bought a Creality printer with a cost of only, say, 15,000. Uh, with the help of that particular component, it is possible for me to uh, print whatever the design I brought in my mind to convey to the students or copper particles. So you have a abundant amount of facilities now, as well as opportunities, so that it is familiarized among so especially with the polymers. I have taken a small example from this source, Hexpec. Is a company which develops parts for automobile industries. You can see the first picture, like shape optimized brackets. You just think about what manufacturing methods, a conventional method could be used. Then this is a casting replacements, and we have a example of ECS for automotive applications. Like, and these are all other examples printed with the help of different materials. Even which is possible to print a layer of few microns, see 1 or 2 microns thickness, by which it is possible good strength can be printed, etc. A few examples: medical 3D printing applications for say this is a spinal fusion cage, and this is a dental model, a prosthetic hand. It's a wearable prosthetic hand, safety equipment, surgical planning. So how to perform surgery before going for an actual surgery. Then drug delivery system. These are the needles. When these needles are dipped in a medicine, due to capillary action, the medicine will suck in. And then when it is pressed against the skin, uh, because of the pressure difference, it will deliver the medicine. So normally we call it as drug patches. Drug patches used external applications. So you can stick on skin wherever you require the drugs. It is very uh, it is printed through 3D printing. Normally we call it as drug delivering micro needles, and these are all the other components printed through 3D printing technology, and these are architected lattice structure, and we have container. So once it is subjected to a temperature, it will fold automatically, and derive the shape like this, like a box. It's a container. So, like, say, if the size is very small, I can fill the drug inside and send it inside the body. So, based on the body temperature, it will open up and release the drug. And this material will be degraded automatically in the body itself. That's also possible. And there are printed by means of 3D printing, and this is see the structure. The structure is gradually varying in order along a particular direction. And this is a mandible template for learning purposes.